crew, Mr. G here today, and welcome to your first lesson on one of the most important units you're going to learn this year. This is this idea of Newton's laws. And before we get to Newton's laws, we'd better talk about really fundamentally what's going on with Newton's laws, and that's always talking about forces. So, a force is really any push or pull. So in kinematics, we deal with the idea that there is acceleration, but what causes the acceleration? That's really the ultimate question, right? And there has got to be some sort of driving force involved with this, or what causes a car to skid to a stop? Again, there's friction involved, which is a force acting against the direction of motion. So all of this deals with forces, so Newton's laws, wicked important to all of these things. It's all about connecting these ideas. Now the unit for force are newtons, and I've told you before that Newton is one of these units that has all of these SI units associated with it, but we've never really shown it. Well, I can tell you now that a Newton is equal to 1 kilogram meter per second squared. And when we get into Newton's laws, specifically Newton's second law, you're going to find out exactly where that comes from. So again, what does this tell you? This tells you that every mass should be in kilograms and every acceleration should be in meters per second squared, or more specifically, time should be in seconds and distances should be in meters. So be sure to have all that straight. Now, in the universe, there are really four fundamental forces that make up our entire collection of forces. First one, and this is the one we're going to deal with this year, is this idea of gravitational force. It's the concept of why are we here on the ground feeling the weight that we feel, and why are we able to walk, and all these ideas. All of this comes down to gravitational force. If you move on to physics 12, you're going to deal with electromagnetic force. The concept of why does a needle on a compass point towards a particular direction? What's going on with that? Then we get into the nitty-gritty, and we're going to talk about the strong nuclear and the weak nuclear force. That's obviously nuclear physics, and that's beyond the scope of what we're going to talk about. We'll talk about some of the effects of dealing with these forces and the idea of the PP chain later on when we're talking about how the sun generates energy. But for now, the big one, the big kahuna, the one that we're going to deal with all year long, is this idea of gravitational force. So, to talk about gravitational force, another way to talk about it is the force of gravity. So, when dealing with the force of gravity, what we're talking about is any two objects that will feel a force of attraction, which will depend on the mass and distance apart. Now, when we talked about the acceleration due to gravity, that is independent of mass, but when we actually are dealing with forces, especially at planetary sizes, it becomes a lot more measurable. The mass becomes extremely important in how much force you feel between each other. Believe it or not, every one of us has a force of attraction between us. So there you go, folks. The mass, again, is going to be in kilograms. And to define mass, we're going to define it as the amount of matter in an object. Okay, so my mass is a certain amount, and your mass is a certain amount, and the mass of this computer that I'm working on is a certain amount. Fair enough. But weight is the amount of gravitational force felt by an object. So we tend to use this word incorrectly. When we talk about our weight, we really should be talking about it in terms of newtons, not in pounds or kilograms. So it's certainly a misnomer when it comes to our conventional uses of words. We know what we mean when we say weight, but theoretically we should really be saying mass. Now, something nice about these ideas is that when we move away from an object that causes weight, so we're going to feel weight because we are attracted to the Earth itself, but say we're out in space, we're going to feel weightless. But does our mass change? Absolutely not. And what if we go on something like the Moon or Mars, whose masses are different than that of the Earth? They're all going to have different gravitational pulls, so our weight is going to change, but the mass, the actual content of our being, will always stay constant. So watch out for those trick questions out there, because there's plenty like that. Now, if we want to actually calculate the force of gravity, we use a simple equation, Fg is equal to mg, where m is equal to the mass in kilograms, and g is equal to the acceleration due to gravity in meters per second squared. Now, some questions, depending on what you're being asked, may refer to this as the gravitational field strength. And be careful when you see that, because they might have it in units of newtons per kilogram. Now I want you to remember that a newton was a kilogram meter per second squared, so if you divide that by kilogram, what you're left with is just meter per second squared. So really you have exactly the same thing. So one important thing to bring up is this idea that g varies depending on the size of the planet and distance to the object. So if we're going to use some examples, if we're on Earth at sea level, then the value of g, the gravitational field strength, is going to be 9.8 meters per second squared, which is the number that you're going to use almost all the time. But what happens now if you go to the moon? Well, the moon is decidedly smaller, both in radius and in mass, and when you find out how to calculate what the gravitational field strength is, you're going to find out that it's actually only 1.6 meters per second squared, about a sixth of what you feel here on Earth. If you move to a different planet, say Jupiter, which is again both way more massive and way larger in size compared to Earth, now you're going to deal with a gravitational field strength of 24.5 meters per second squared. And of course, the granddaddy of them all, if for some reason we were standing on the surface of the sun, if we could survive the fact that we've probably vaporized, there's a gravitational field strength of 274 meters per second squared. So again, all of these differences in gravitational field strength, you're going to learn how to actually calculate these and find the difference between them. But more importantly, just realize that our weight is going to change, but the mass that we're going to use in our calculations will always remain constant. So just make sure you know which g you're dealing with. So let's say that I wanted you to calculate what your weight was here on Earth, the moon, and Jupiter. Let's say that you have a mass equal to 100 kilograms. I'll just pick that number because it's super easy to do the math with. I have no idea if you're 100 kilograms. No big deal either way. But if we're talking about now what your weight is on Earth, well, Fg is going to be equal to mg, which is going to be equal to 100 times 9.8, which is going to give you, now you see why I picked 100, 980 newtons. So if you were 100 kilograms, you're not going to say your weight's 100 anymore. You're going to say your weight's 980 newtons and really blow them away. Now, you want to lose some weight? Simple. Just move to the moon, because watch what happens now if you're on the moon. You use the same equation, except this time, instead of 9.8, we're going to put in a number of 1.6. And when that's the case, you end up with an answer of 160 newtons. So just like that, you feel substantially lighter. So again, where you are is going to matter greatly. And finally, if we're going to be dealing with Jupiter, and I'm going to write it, let's put it up here. If we're on Jupiter, Fg is equal to our mass times our acceleration due to gravity, but this time it is way larger, and you're going to end up with a weight of 2,450 newtons. Ladies and gentlemen, let's just call it like we see it. You would be crushed, because there's no way your body would be able to hold up to that. So, good thing we're here on Earth. The moon might be more fun for jumping and throwing stuff, but otherwise you can't breathe on the moon, so that's a problem. And Jupiter, of course, is definitely a ball of impending doom. So, you've learned about the different types of forces, but more specifically the idea that we're going to deal with gravitational forces. So Fg is equal to mg. Do not forget this in a couple lessons when we bring up the general form of that equation. Far too many people forget that this all came from somewhere. So good luck, and we'll talk to you soon.